Hi everybody, welcome back to this new video episode for the STM32 tutorial. And within this video, we will dig further regarding the chapter of the ADC and having a more comprehensive functions and new option that will help us. So what we are going to do first is to create a simple function that will increase the number of readings that will give your ADC and the STM more accuracies in your readings. But also we will see those functions, so we are having more accuracy, but that will consume more cycle time from your microcontroller, and we will see how we can read that and understand that and how to improve that. Then we will create simple functions that will help you a lot in the interpretation of your readings. So if you're interested to deepen your knowledge and to improve your usage of the ADC of a microcontroller, this episode is for you. Okay, so let's quickly take an overview about how the chapter is composed. So first of all, we are going to review the circuit. We changed a little bit the microcontroller and we added some stuff, so it's good to know what we are going to use. Then we are going to start creating this pin analog cycle set. So this is the function that will define the number of cycles that the ADC will be running before providing or giving back the result. And then we will have a quick cycle time analysis, and this is to review how long it will take if we increase the number of cycles for the readings. Finally, we will go through the pin analog reading division, and this one is the function that will help us to modulate better the type of input that we get from the ADC. Then we will have a live test, so we will review within the test how we can use those functions to a very interesting way. Finally, the microcontroller we are going to use is, for this time, the board is the STM32 F4VE, the Chinese board, which is really fantastic one. Honestly, I like using it a lot. And the microcontroller unit is the STM32 F407VE-T6, and we were using the GT before. Okay, good. So let's jump to the next part, which is regarding how the circuit is the circuit review. So let's quickly take a look at the circuit. So first of all, we do have our slide potentiometer. I should remember this now. So this is our slide potentiometer. So let me make this video a little bit bigger, or the picture on this one a little bit bigger so you can see it better. So that's the sliding potentiometer, which we do have here. And also we do have a rotary potentiometer, and we will see why we are going to use two later on in our live example. So the PA1 pin is connected with the slide potentiometer, and the PA4 is connected to the rotary potentiometer. So we are adding here a connection from PA0 to the logic analyzer, and this is to study the time analysis for the PA1. And after that, we are also adding the PA5 to also as an input for the logic analyzer to study the time, how long it would take to make the conversion for the PA4. Okay, so those are the part of the circuit review. We can now hide the image and go jump directly and start. So our starting code, or the beginning of our code, is the same code we finished in the previous video about building the basic functions of the ADC. So this is exactly the same code we created. However, don't forget I have changed the microcontroller, and then I needed to go to the device here and select a different device, then updated all the things regarding to the compiler and C. And also in this example, and let me show you, also this is something worth noticing, I'm not using a normal ST-Link. This is a kind of a choice, so for you to know that we can use a different type of code loader, and this one is called a G-Link. A G-Link is a more general code loader, which is better adapted for whatever microcontroller with the ARM microprocessor. So this is just a parenthesis, and the code and what we are going to do would work exactly the same if you do have an ST-Link. This is just a choice to enrich how you do that if you do have a JTAG connector. So here I'm going to set it up, and I will be selecting my G-Link here and go to setting. And for the setting, there's sometimes both JTAG or SW. Use the SW connection. So you see here that my JTAG is already connected and identified, and also that my ARM microcontroller is also my ARM microprocessor or ARM-based microcontroller has been detected. And as a final step, what we can do is just let's load the code just to see that things work properly. So you see that the loading is working quite well. And if we go for the debug mode, here we can see here also the code. So if we run here and I bring back the video for this one, make it a little bit smaller like this so you can see what's going on. So by moving, now I am moving the rotary one, you see that the value of the resistor, the rotary potentiometer is also changing, which is working properly. So I am able to debug. And also if I move the sliding potentiometer, this is also working. So we do exactly have what we need from a JTAG, same behavior as a G-Link. Okay, so let's hide the camera, close this one because we don't need it, and we can start jumping to the ADC library and start building something very helpful. So let's close everything, and this is all what we have created in the past code. So we can start creating our function, which is the pin analog cycle set. So it's a void function. There's no output expected. So pin analog cycle set, and for this one char we need the ADC, so we need to select which ADC we need, and after that for the int we need to have, as usual, the port pin selected, and finally we need also to select the char that we would like to use. So char cycles like this, and we can start our function. As usual, we need to map our channel and also our ADC. And just to get back a little bit to understand how this is working, so let's go to the STM32F4, the ADC register, and we go here. So those are the registers. There's two registers that are controlling what they call the sampling rate, so the number of samples that the ADC will perform before delivering or flagging the end of conversion. So this is giving more stability in the numbers that we get. And from that perspective, we do have the initial one, the reset value 0, 0, so it performs 3 cycles, where at the 1, 1, 1, it performs 480 cycles. Okay, and there's another structure for these registers. So there are 2, and they are covering up to 17, 18, or actually 19 channels, where up to 15 are the normal channels, and the other one are the channels connected with the temperature sensor inside the microcontroller. Okay, so you can see that every channel is controlled with a 3-bit for each register, and there's a portion of 3 bits. So we will need to have a certain logic that will be mapping those channels and the bits, so we can immediately or getting that directly. So we can go back to our code and start by getting the channel, and we already create a lot of things related to that. So we can check where we here, not this one. So I think we do have a good code about the channels that we can get directly. Yes, this one we can put here, and we put for a char channel will be equal to ADC pin, and also we will need to have the register or the pointer for our ADC. We can use the ADC init function, so we can inside it like this, and we can define as an ADC type def. ADC type def, and all this is kind of a free code coming from the previous function that we can use immediately. Okay, to start this conversion, first of all, we need to go for the ADC, ADCX, and stop the our ADC. So we put equal to 0, quite a direct 0, and not equal here, but that's a pointer to CR2, like this. And after that, we start selecting the channel that we need to use. And we need to put a small condition. So we will put here, if the channel is greater than 9, so, and which is here the same logic, just to go back on, not this one, and where is it? Here. So if the channel is greater than 9, we will need to update this register, and we need to do it in a quite a special. We need to, this 10 is equal 0, so we need to control that a little bit. But if the channel is less, so we just multiply the channel by 3. Okay, so let's go here. So we say if the channel is greater than 9, then what we can do, so our ADC X here, and we need to check the sampling STM32 is or equal, like this, sorry, it's actually 2 functions. So let's show which one is changing it, so or equal here, and that will be the cycles that we input, and we will see how we will manage that later on. And the cycles will be pushed by, so let's open this one, we will put channel -9. So channel -9, so if it's the 9th channel, it will be a 0. And then we multiply, so actually this one is greater than 10. Because if we go back here, here it's a channel 10, channel 9 is here. Yep. So let's go here, -10, and we multiply the whole thing by 3. So whatever the values are, let's confirm. There is no need of this one. And let me zoom for you guys, because I guess this is not good enough. I hope this size is much better. So channel, so this one, let's check. So we do have this, and I think we need to close again, and we are good. Let's check. Yeah, we are good, but still something we need to take care of. So this is to update it. However, if we have used this one before, what we need to put first is here the or equal, the opposite or the tilt of, and not the channel here, but it's a 1, 1, 1. So it will be a 1 + 2, 3 + 1, it will be a 7. Not this one. Cycles here, well, that would be a 7. This is a, let's put it as a hexadecimal just in case, a hexadecimal 7. So this one, when we apply or and equal the tilt of this one, what it will happen, it will go to here, and that will clean or reset the whole register. So when we will put our OR cycle, everything will be quite well. Then else, you got it. So now it's very simple. So we don't need the -10. We just put this one here like this, not -10, just like this. So if this channel is less than 10, we just go through that one and we can apply this. By using so, we are setting up our channel to be to create or to book the cycle of readings. Then when we complete the whole thing, what we can do is just run the ADX. So we go here. We need to go first here, apply equal to or equal to 1, we put here, we run it. And where is it? So we put or equal to 1. We can get some free code from here. We are repeating the same thing, so we need to wait until the ADCX, where is it? Not this one. We need to go for the analog set. We still need to wait. Not even this one is in this one, within this one. We need to keep wait until our ADC is ready. So this is really starting the ADC. Waiting the ADC is good. And then we can put the 1 here to start operation. So here, where is it? And I think we are good. So we just apply this one again. Where is it? This one again. And our ADC is completely now transformed and changed. Okay, so we do have this channel pin analog set. So now one of the things to avoid any mistake with the cycles, what we can do, so let's go back here and show you again. So you see those cycles here from 0, 0 to 3 cycles. So it's from 0 to 7, and we have that number. What we can do and make your life much easier. And again, this code is available on GitHub. So you just have to follow here and understand what I'm doing. So what I'm going to add now, I already prepared the snippet. The snippet is here, and just define those cycles. So you just put this cycle number and that's all. Okay, good. So now we do have everything defined, and you know me, I like having some optimization. So let me save this and close it. So open this one, and for the ADC one, what we can do and get we can go here, change, and we call a function. So we can use a different function. We can call it pin, and sorry, it's a void function again. So the pin, then ADC, we call it RX cycle, or yeah, I think cycle would be good. Yeah, ADC, or not even RX, just ADC cycle, like this. And by doing so, we just open this one and we put two things. So only the int and the cycles. And inside it, we just have to add, no, not this one. We just add this. So that will be doing this. And for this one, we will be using the ADC one. So it's a very kind of lazy way to have some functions ready for you to use for whatever the pin. So we take this one, we copy it into, and also you can create the ADC2, ADC3 at your, but I don't like this cycle with the E here, mistake, and we called analog to digital. Okay, AD cycle, that has more punch, I think. So we go here and we bring it to our header. We add this function here. Let's add this one, and we are good. So now we go back to our initial code, and what we are going to do is we can put the pin AD cycle, this one, and for PA1, and we would like to set up as the maximum, just to see how big is the difference. Okay, and to understand the difference between of them, at least from time perspective, what we can do, we can start by setting up. So I think we can go now to the next chapter, and here we are. So cycle time analysis. We can start here. So by setting up the both pins, so pin output set for the PA0 and also the PA5. Okay, so those are set as outputs. Good, so now what we are going to do is taking this one, so pin output, so sorry, pin right, like this, and that will be the PA0, and we would like to have it high or on. Then we would like to shut it down and put it as off. So we will be reading that on off time, knowing that the time for the pin to get on is in nanoseconds. So it will be really small compared to what the operation of the ADC. So we can copy again the same code and run this one again. So this one is on for PA5. Then we put it as off for PA5. Okay, so we do have everything set now. So let's just save and build to see if the code is working well. So it's a zero error, zero error and zero warning. So our code is quite good. We can start loading our code and having the time analysis. So let me bring the software for the time analysis. Let me try to make it as big as possible so you can read. And I'll be starting now checking the data. So this is what we do have here. And let's see what's going on. So I will stop here and see how long it takes for PA0. So PA0 is taking 126 millisecond to read the data, where it takes 83 millisecond to also read the data for the PA4. Just to as a reminder here. So and if I bring it like this and I go here and just bring this one, so the PA0 will be taking 126 seconds, and the PA5 is 83 seconds. So let's go back again and comment this one just to check that everything is aligned as we want. So let's load and let's run again the logic analyzer to see. So now you see PA0 is taking only 65 microsecond. It's not even millisecond, where the PA4 takes a little bit more. And this is because there's the conversion happening and a change. But now let's play a little bit further. And this is just for fun to see. If you remember, we created an ADC clock function to make our microcontroller much faster. And we do have this clock of 168, this one. Let's boost the power of our microcontroller and see what will happen. So let's clock speed. So this is for the 400, for the 407, so clock. Okay, something is not implicit declaration is not valid. So let's go here. Did I made a mistake? Where is it? Yeah, I know, because I need to include it here. Include clock. This should fix everything. So let's build and load the whole thing. Now we do have the maximum speed of our microcontroller. And let's see. So you see it's already much smaller. And the reading cycle, the normal reading cycle is 6 microseconds. It's fantastic. Where the other one for the P4 that takes a little bit more time, it's 8 microseconds. So now let's change again and increase the number of the readings, which is this one. So we're increasing the number of PA1, the number of readings. So let's build here and load the code. And we can get a different number now. So you see, we have 17 microseconds and still 8 microseconds for the 4. And let's play a little bit more and see how how this happened for the this one. So if we put like this, so we increase the maximum number of cycles for the PA4, and let's build. So now let's read and see how long it will take. So now for the 4, it's 19 microseconds. So just for you now to see what is happening from the perspective of time analysis and how this is impacting the performance of your code. So there's accuracy, performance, and you need to choose which one is your target and which one is the most suitable for you. So finally, before we got there, let's comment for the PA4. Let's build and load again and go for the debug mode just to see how the values are going to behave. So we do have the PA4 is a kind of a like 3 cycles only, where the PA1 is 480 cycles. So the PA1 is connected to the slider potentiometer, and you see that the variation here is really small. So I'm moving, so let me show you the video quickly. I'm moving the slider, I'll be moving the slider now, and you can see that it's really small. The changes is really small, where from the potentiometer perspective, when I change it, so let's see, we do have a little bit bigger variation. But so for the noise at the potentiometer, the slider potentiometer is smaller than the rotary one. Okay, so that was just a good view of what's going on here. Then, so now we have completed our cycle time analysis. We can create another function that I find extremely helpful for so many applications. And let me just go back then here. And this function, I usually call it the kind of division function, or the function that provide me a certain division that I would like to get. So this function will be built on the reading function. So I'm going here, be going then here. So the analog read function. So let's go here, and I'll be creating, so I call it int and pin analog. So as usual, I will be creating a general function and then orient to a certain ADC to make life much easier. Analog Rx and here div. For that, as usual, we will need to add the char for the ADC and also the int for the port pin. And finally, also the division that we would like to have. So this one, we call it the int div. And you will understand how interesting this function can be, and that will give us a lot of free code and optimization. Okay, so what we need to do, as usual, is we need to get our ADC. So let's call it how to make it. So for this one, let's quickly get the ADC. We just need the ADC here. Let's get the ADC, and we make one check. So for our check, if someone put a division, and division is, so our result right now varies from a 0. Let me zoom in a little bit so you see it better. It goes from a 0 to the number of 4095. So that's a 12-bit range, but sometimes we would like to see it differently. And we would like to see it from 0 to 100, or 0 to 360, or whatever the value. We would like to see it depending on the perspective, the physical perspective that we are managing. So here, first of all, if the user is putting div equals 0, which is meaningless as a thing. So if a div is equal to 0, then we take a little bit of step here and a little bit of initiative and say, no, man, we will take a div is equal to 1, and that will be meaningless at all. But after that, so else in that one, so if we check our ADC. So we need to check if our ADC is greater than the div itself. So if we go to ADC, our ADC value here, the ADC value, just a moment. Where is it? So the ADC, actually we don't need this one, to be honest. We can get an int and we call it ADC val like this, and we put equal to the pin analog read. Pin analog read, where we add the ADC and the port pin like this. So we initially read this value, and so this is the initial value. We get the value that we need to have. Then we check, this is important, check if the ADC val here is multiplied by the div that we added together and divided by the maximum range. So this is the maximum range on this one. If all together, the whole thing together, let's add another one here, is greater than the number of division that we do have, and that's sometimes there's a rare case that happens, we can directly return the div itself. So we give the maximum range. So this function will be kind of, I would like to have 180 division, but if the result is 181, which doesn't make any sense, and this happened because sometimes there's an error happening with the result of the ADC val, then we return the maximum. Else, what we will return will be this value here. And this is a rule of 3 that will provide us, so where is the mistake? Expected, yes, I don't need this. Or I will cover with both, like this. Okay, so now we created this function. As usual, I will be creating quickly another function that will make things much easier, and I will call it void pin, and I will call ADRX and division. And this function will be needing only the number, the int, and the division, like this. Here, and we'll be needing, so on this one, it's not a void, it's an int, and it will return this function. Not this function, sorry, this function here. Okay, so and this function, so the ADC will be my ADC1, and port pin and division will not change. Okay, follow with me. Good, so we do have this one now, this function ready to be used, and we are going to start our live test and see how interesting this function can be and helpful to manage some of the code. Okay, so all good. And now, so let's go back to our main code. So instead of, for reading the potentiometer, so let me show you quickly the potentiometer or the sliding potentiometer. So it's kind of the X position here. So, and instead of reading, we would like to read only the voltage, and this is what we will do. We can also check the X position. So what we can do here is getting a few other type of data that will be extremely helpful. So let's go here quickly, and we call this one, we call the P1 voltage, and it will be in millivolt. And also we would like to have also the slider for the P1, the slider in P1, and we would like to read it as a millimeter, so we can read the millimeter position. This slider, by the way, let me show you, sorry, I was hiding here. So this slider is a 30 millimeter, by the way. So we can take that one as a maximum. We can also add for the rotary, we can take also the angle. So we can get the angle, and it's a 360, so it can go through all itself. So let's save this and start getting those ones. So this is the L of the potentiometer. This is just the value. But if I would like to take the, as we said, like let's take this P1, the voltage value, and we would like to read it in millivolt. So this will be equal to the pin ADRX division. So that will be the PA1, but I would like to read it on 3300. So this is 3.3 volt or 3300 millivolt. Where in the other hand, if we go for the slider millimeter, how far is the slider from one extremity to the another? So I can copy this again and read here, and it's a 30 millimeter, where at the end we can take my angle from my rotary potentiometer here, and that will be equal, so bringing this one to check on 360 here, and this will be for the PA4. Okay, so now we have all the code ready. So let's save, build. We do have 0 error and 0 warning. So let's load our code and go for the debug mode quickly. And then what we need to do is to add those values to our watch to see what's going on. So we go here, and we go here too. So we have all these values, and let's show them in a decimal way, not in hexadecimal, so we can understand better. So now let's start running the code. So we do have those values. So let me bring now the camera, and we start understanding what's going on. So we start with the first value here, this one, the P1 voltage, the millivoltage. So now you see my potentiometer is almost at the maximum, and it's reading almost 3300 millivolt. And if I move to the other side or in the middle, so you can see I have 1.5 volt or 1500. And you can see also the distance in millimeter here. So it's a 0. My pointer position is 0, where here my pointer position is 29 because it's almost 30. This, yeah, you see here it's sometimes 30, 29. On the other hand, if we take a look to my rotary angle, so now I'm moving my rotary angle, and you see we are at 300, almost 360 angle. And if we go to the other side, totally at the other side, we go to 0, and we can get the angle of the rotary. So by doing so, we can immediately get the proportion or the relativeness of the position that we need, or the physical layer that we need. Okay, that was the last part of today's tutorial. I hope that everyone has enjoyed this. Thank you a lot. So for the next episode, we will be viewing the interrupt and also the watchdog. Again, thank you so much for following this episode, and wish you a wonderful wee day. Bye-bye.